Hello, good afternoon, hi. Woo, SREcon, right? Yeah. So what would happen if all of the machines you run on, every single one, whether they're in the cloud, in a data center, or under your desk, restarted right now? Like, sure, you'd have an outage for the duration of the reboot, which is what, like 2 or 3 minutes on a Linux machine. But how much longer would you be down? Hi, my name is Tanya, and I'm a site reliability engineer at Google, working on dependencies and bootstrapping and low-level infrastructure, mostly right down the bottom of the stack. But what does that even mean? I had this great conversation with a student about this once. I was giving a talk at New York University and to some CS students, and afterwards, one student came up and she said, "What can you tell me about Google's CMS?" And the slides didn't move. No. Seriously? Seriously, we're going to do this? Okay, we're going to do this. And I said, I was sorry, but I honestly didn't know. I've been working on infrastructure for more than a decade, and I don't know anything about front-end stuff. And she said, oh, sorry, I mean content management. And I'm like, yeah. And we just stand there for the longest time looking at each other, like, what is the language difficulty we're having here? Now, bear in mind, this is like maybe a second-year student. She's new to CS, and I've just spent the last 30 minutes talking to a room, being all like, hello, I'm a serious industry professional who is bringing you all the great wisdoms. So kudos to her for pushing on with this conversation and not just being like, thank you very much, and running like hell, which I would have done at the same time in my career, or possibly now. But she really made me think about this. Eventually, she said, isn't the CMS the back end? And I said, yeah, I mean, kind of. Okay, yeah, you're not wrong. It's just, I'm further back than that. And her eyes went really wide, I swear, and she said, there's further back? Yeah, there's further back. Everyone's back end is someone else's front end. It really depends on where you stand. There's this parable in various Hindu and Buddhist texts about trying to identify an elephant by touch. You have a completely different idea of what this thing is, depending on where you're standing. It's a wall, it's a fan, it's a snake, it's a spear. Similarly, it's a back end, it's a front end, it's a platform, it's a user. It's probably all of these things, and more. Anyway, I think of myself as being right at the bottom of the stack, caring about job control and machine installation and what time everyone thinks it is. But then the core networking people are probably like, oh, hi up there. And the power and the cooling people are thinking the same about them. And below that, someone had to pour the concrete. So you see what I'm saying? Anyway, all of those caveats aside, I would usually say that I operate at or near the bottom of the stack. But this story about where the CMS sits really entertained me at the time. And I told it a lot at parties, which made me very popular at parties, as you might imagine. And it took a while before I realized that I had the point of my own story completely wrong. See, I thought the point was that the very important infrastructure that I work on is just way more complicated than everyone thinks, and way more important. And that it was wrong for the student to take the part of the universe she knew, split it in two, and call it the front end and the back end. And it wasn't for a while until I realized that it was just as wrong, or just as right, for me to take the infrastructure that I knew, call it the back end, and say that everything in front of that is probably the front end. Because it's a whole lot of it depends. We're both right, we're both wrong, depending on how you want to look at it. Because increasingly our stacks are really complicated. When we're talking about all of the systems through hardware and power and networks and infrastructure and processing data and applications and user-facing systems and client-side, unless you have the simplest site in the world, nobody can really know all of it. We know the tech that's adjacent to us, but we have to make some abstractions to make sense of the world. We just can't function otherwise. So here's a picture of your stack, no matter where you sit. Here's a mental model. There in the middle, that's you. You know what your service or your code does. Probably, right? You know who your users are and what they're doing. No, you don't, but you like to pretend you know who your users are and what they're doing with your system. And you know your major direct dependencies. And you usually don't have a perfect picture of everything else. And that's okay, that's how it's supposed to be. We humans specialize, we go deep. We make contracts, either social contracts or expectations, or actual formal SLAs with the people who run the stuff below us. They say they can give us some number of nines, or that the concrete will hold some number of kilograms, and we trust that, and we roll that into the contracts that we give to the people above us. That's society. Like, most of us don't know in detail how water gets to our house, or what twisty light bulbs are actually made of, or where breakfast cereal comes from. We just trust that these things will continue to flow. But in a disaster, the societal model fails us in two ways. One is that as much as we trust that the electricity and the water and the breakfast cereal will continue to flow, we might keep candles and bottled water and other breakfast cereal in our house. We have a plan for when things lower than us in the stack go away. And that means we have to know something about them. That's the fallback plan. The other thing is that these things we depend on, sometimes they depend on us right back. And that can be a bootstrapping problem. I love this tweet from Zeynep Tufesti. Huddle around the fire, children. I'll tell you how interdependencies and complex coupled systems took it all down. Eat your cockroaches. Can interdependencies and complex coupled systems cause our entire society to collapse and not be able to get back up? I don't know, but it is a really fun thing to debate over beverages. But can they cause a site to be completely unrecoverable after a disaster? Definitely. So I'm going to talk about three things today. First, fallback plans, why they're inherently dangerous, and how they break the societal model, so we don't always get the nice, clean abstractions that we're looking for. Then I'm going to talk about dependency cycles and bootstrapping, and how not globally managing our stacks can get us into trouble, and can make it very hard to recover after a disaster. Then finally, I've got some solutions for both. And fair warning, I'm going to try really hard to convince you that you should start managing your dependencies right now, even if you don't have very many of them, even if you think your site or your service is too small. I'm going to try and convince you that it's still the right thing to do. Let's start with fallback plans. Fallback plans are the things that we do when our regular operations aren't available. They're things we don't usually do, and they're things we don't want to do, but sometimes we need them. Anytime we think about what we'd do if some piece of infrastructure went away, that's a fallback plan. So some examples of fallback plans, like serving from a cache of last known good data, or starting up with a different configuration to bypass some piece of infrastructure that just went away, or booting up the backup generator, or recovering from tape, or failing over to a secondary site, or getting a key from a fire safe. Whatever it is, it's not what you usually do. Your code and your services and your human processes, they usually do something else. And chances are it's been a while since you've done this thing. And that makes fallback plans the scariest, most precarious piece of your infrastructure. At the time when you need them, you need them. They're your last resort. They have to work. But by design, they're less used. When you use a fallback plan, you're using something that is inherently less tested, so it's more likely to have bugs that you just haven't stumbled upon yet. And when your infrastructure is changing really fast, it's hard to be sure that the plans are even still up to date. Something that worked when you tested last time might not have survived the 10x growth that you had last quarter, or your fancy new authentication protocol. It just might not work anymore. I'm going to talk about the perils of the fallback plan by looking at two of the most common fallback plans for major disasters: backups and DR sites. Backups. Take a copy of your data and you put it somewhere else. Maybe it's on another server, we would hope. Maybe it's read-only in a storage system, maybe it's on another site. You know, it depends what the problem is that you're trying to protect against. You probably, you think through some scenarios for what could cause your data and your backups to be lost or corrupted at the same time. And maybe you've got full backups and incrementals. If you're responsible, and I think this is not controversial anymore. I think most people in 2017 test their backups. My friends in Google's data integrity team, if you don't tell me. My friends in Google's data integrity team always say, you don't need a backup plan, you need a restore plan. There are some ways it can go wrong. For example, I was telling a friend about preparing this talk, and he was like, oh yeah, funny story. He had just found out that the backups he'd been faithfully taking using file system snapshots for years would never have worked, because they depended on some piece of metadata that was held in memory that was mapping the tables to inodes on the disk. They were just completely worthless. Untested fallback plans are a gamble that you're not likely to win. And this is certainly true of backups. If you haven't tested that you can recover your backups, you don't have backups. And that means more than just recovering the data. If you can recover the data, but you didn't back up the decryption key, you don't have backups. If the data is in a proprietary format and you can't install the application that can read it back, you don't have backups. If you have incremental backups, but your application can't handle backfilling incremental data, or if you have full backups, but you don't have enough network bandwidth or disk to get the data to where it needs to be, or if recovering backups takes a long time and your customers get angry and they stop paying you and your company collapses and you go out of business, you don't really have backups. But the problem is that testing backups is incredibly tedious, and people will cut corners because we're humans, we're lazy, it's what we do. If your fallback plan relies on human willpower to keep it up to date, you've already lost. So the recovery tests need to either be automated, incredibly simple, or both. Backups are necessary, but most of the time we want to survive more than just data loss. We want to keep the service running in the face of a major disaster where we lose an entire site or data center. So another popular fallback plan is the failover site, a replica site with a copy of everything or most things in it, and it's ready to go when we need it. The passive failover site is a great example of anti-patterns in fallback plans, which I will enumerate in the form of questions, which I invite you to consider while thinking about a DR site or failover site that you know and love. Question 1, and we have to be honest with the answer here. Is the failover site real, or is it a decoy pretending to be a failover site because some VP got nervous 5 years ago? Like, you did it enough to close the bug, but nobody's really got time to make it really solid. And it's enough like a real site to make everyone feel kind of safe and secure, but if you had to use it, well, it would be useful, probably. A fake plastic DR site is almost worse than none at all, because it gives everyone such a false sense of security. You know, if it's a social contract again. If this thing exists, people will assume that it works. If it's not really real, it's kind of better to admit it and at least force everyone to behave more carefully, rather than waste time in an emergency. Question 2, is it bit rotting? It's definitely bit rotting. How badly is it bit rotting? If your sites are managed only by perfect robots, then you have some chance of keeping it up to date. And config management has got us closer to the perfect robots world, but we're not all of the way there. But most likely you employ some fallible humans who will make some changes and not make the same change in the failover site. And if the idea is that you can completely lose your primary site, like it can just go off, then every single thing in it needs to be available in the secondary site and up to date. Authentication and documentation and monitoring and whatever, live versions of everything. It takes serious processes to make that happen. The flip side of that is that you can be too recent. Like, have you seen active passive databases where the backup for the database is in another site, but it's kept up to date by replaying every single transaction that goes to the primary database? Like, this is great if you're trying to survive a power loss, but it's not really good if you're trying to survive someone pushing a schema change that blows away the database. Question 3. This image is from my Pinterest board, apartments I would be terrified to drink red wine in. Question 3, has anyone ever used it for anything real? Again, this applies to failover sites, but also to every other kind of fallback plan. If you've got a fallback plan that you're not regularly using, you don't really have a fallback plan. And I know I said that about backups, but it's still true. And I mean really using it. Like, you can bring up your dev environment there or whatever, and everybody's happy. But until you actually fail over, you don't know if you can restore keys to there and deploy from there and run monitoring out of there. And is it secretly calling back to a whole lot of hard-coded services in your primary site while you do it? Until you failed over and back a bunch of times and turned off the primary site, you've got to assume that something in there isn't working. Another story, I love this, from a friend who works for a big online clothing company that typically ran out of the East Coast of the US. They tested failing over to their DR site on the West Coast of the US. Now, all the machines were on local time, so 3 hours different. And when the database started replaying transactions, some of them were in the future. Didn't like that. It threw up on its shoes. It was a horrible time for everyone. And this is why we do real-life disaster tests before we need them. All right, this is SREcon. So like half the room is here like, DR sites, are you from the past? I have lots of completely replicated sites. If one failed, I would elegantly drain it. Look, I'll do it from my phone right now. We saw that with Shopify. Emil from Shopify did that yesterday, and it was really freaking cool. Not from his phone, but that can be next year, I guess. The best fallback plan is not needing a fallback plan. So this replicated future is really awesome. Like, maybe you need a human, or like maybe your 3-year-old to manually take action and shunt the traffic from one place to another. Maybe intelligent robots who solve so many of our problems will notice this one and work it out. But there's no bit rotting because everything's in use all the time. You take the same pathways through code and systems and processes that you always do. It's just a capacity problem. We're used to capacity problems. It's a common operation. It's one of the beautiful ways our systems are more resilient than they used to be. So does that mean you don't have to think about disasters and failover if you're replicated? Nope, because dependencies. Dependencies, I love dependencies. Dependencies between services means that we can't think about and replicate running binaries in isolation. we need to think about how everything is connected to everything else. We can look at big distributed systems like a graph with nodes and edges, where the nodes are individual binaries or services, a bunch of binaries as a service, and the edges are the dependencies between them. Those edges are where all the action happens. It turns out it's where the really special failures happen as well. So I should clarify what I mean by dependencies. I'm not talking about build dependencies, where you need a library to exist so you can build and deploy your binary. You may remember, maybe vividly and late at night often, when someone deleted a module from NPM last year and broke like thousands of packages around the world that were depending on it. That was pretty exciting. That's a build time dependency, and it can totally ruin your day when you can't build and deploy your binary, but it's not what I'm talking about right now. I'm talking about something else, dependencies between running services or microservices. I'm talking about what will happen when one binary or service can't start up or can't continue to work unless the other is already running. Like, say you've got two services that both need currency converters. Traditionally, we'd put a currency converter into each one, maybe, and maybe they would use the same library if they're in the same language, and then you would make sure that both of them got exchange rates and they both couldn't do currency conversions. But in the microservices world, it's more common to set them up to both send their requests to a third service. So now only one service cares about exchange rates and currency conversions and so on, and the others just need to know how to talk to that. So how do they talk to it? There's like a bunch of popular ways. There's exchanging JSON or protobuf over HTTP. Apache Thrift is one. And Google has open sourced a remote procedure call library called gRPC, which Gabe and Grania talked about on Wednesday. That was a great talk. But here, the service owner, whoever's running the currency converter, decides what methods are available. Maybe convert and get exchange rates, something like that. And the people using the service, the salespeople and payments people here, they call methods that do the same thing. But secretly, not very secretly, but maybe not as transparently as we might have had before, this is all going across the network. You're using a library, but it's all going across the network. It might be easy to forget that the currency converter is an external dependency. The more you've decomposed your services into microservices, the more dependencies you have. And the more dependencies you need to keep track of. The graph of your system can get really complicated. The client libraries you use can change over time, and they can get new functionality or different backends. And the things you depend on can completely change their implementation to depend on other things. And you will never know, because by design, you don't need to know, right? But they can now depend on services that you prefer that they didn't, like maybe you. So you can pick up new service dependencies you don't even know about. Equally, remember your service is a dependency too. You can pick up users you don't know about, who think that you're offering more reliability than you think you're offering. So stable systems, get things built on top of them. So you may think of yourself as a not very important front end, but other people may find out that this elephant has become a critical back end. I really apologize for the critical elephant back end joke, but it just cracks me up. If you don't know who your users are, you don't know what reliability is expected of you. And if you don't know what your dependencies are, you don't know what reliability you can offer. Because unexpected dependencies are a source of outages. A service cannot be more available than the intersection of all of its critical dependencies. If you don't know or you don't remember that you use some system, you're not designing for its failure, and all of your SLAs are lies. But even more than that, you need to know your dependencies because of your place in the stack. It's the social contract. You owe it to society. And this is why. It's because everything I said at the start was a lie. There are no front ends or back ends. There is no stack. These are lies we tell undergraduates. In most sites, what there actually is a deranged tangle of things that grew organically and that are connected to each other in whatever way was convenient to whoever was trying to launch at the time. The stack is more like a drawing by M.C. Escher. The deranged tangle can be very hard to deal with day to day. It decreases your velocity, and chaos causes outages. But it's really especially hard to deal with in a disaster. Because when we plan disaster recovery for a site, we plan it in the same small sections that we operate in. We assume that the things below us will continue to exist and have their own plan, and the things above us will continue to exist and have their own plan. And we plan our own part. And dependencies can make all of that fall down. Once systems get really big, it can be hard for humans to reason about them. And it's easy for cycles to creep in. Like system A depends on system B and system B depends on system A. You'll probably notice that. But if A depends on B, which depends on C, which depends on D, which depends on A, you might not see that for a long time. You might not see it at all. The worst cycles are the ones you can't recover from, the ones that completely lock you out from the control plane of your service. For example, maybe everything is blocked waiting for the network to come up, but you can't fix it because you have to get to a network device that you can't fix because the network is down. Or maybe a bad config push has stopped you from being able to make any changes to your config push system. And you can't push another good config push because the config push system is down. Or maybe your IP addresses have changed, and for some reason you've hard-coded the old ones in your build system, and you can't change that hard code because your build system is down. Or maybe your startup process for everything is really arcane, but also incredibly well documented and up to date, and the documentation is great in the documentation server, and that's one of the things you can't remember how to start up. You can get wedged. You can be unable to recover. We can think of huge interdependent computer systems like machines, like one huge, big, unwieldy machine, assembled over decades by many people who didn't know each other. And we bolt extra things on the outside. We replace bits as they're broken. But there's always some part that's running. We build them, and then we don't expect to ever build them or turn them all off and on again at the same time. A metaphor I've heard and liked for this is we're like cave dwellers who can't make fire, but we can light new fires by running with a torch from the last campfire. But what happens when the campfire goes out? Here's that thought experiment again. Suppose every machine you run on right now, while you're here watching this talk, rebooted. And by the way, I hope you're saying, no, that can't happen because failure domains. We're completely sorted. But humor me for a moment. Are you certain that your systems, your sites, your machines don't share anything that could cause everything to reboot or restart, or get wedged, or get compromised in a way that would need them to all be restarted at the same time, all at once? Like, could they share a power supply manufacturer, or an operating system version, or any low-level library that contains the word halt, or an authentication system, or a config push mechanism, or an operator who's really bad at scripting, or an operator who's really good at scripting who hates you? And are you sure that your infrastructure providers, all of them, are sure of the same thing? A global restart can happen. Suppose it did. How long does it take you to be back to normal? Let's imagine this is the luckiest day of your life. There are no hardware failures. Everything comes back up. If you're running a 4.9 service, you can afford 4.38 minutes of downtime per month. And your machines can probably reboot in 2 minutes. So you're golden, right? In an ideal world, everything just starts back up in the same manner and starts running and recovers beautifully. But systems depend on each other. So say you power everything back on, and your front end sits there waiting until storage is available, which is a completely reasonable way for a front end to behave. And your storage is waiting for your decryption keys, which is good, as it should. And the decryption is waiting for the authentication system to make sure that it should decrypt. The authentication system is using some keys that are in your storage. So these four systems are all sitting there waiting for each other to come online. But at the same time, the job control system would like to pull data from the config system to know what binaries to run, but the config system is trying to do a master election and is waiting for the consensus system. The consensus system wants to make sure it's got up-to-date software, so it's got to call out to the service registry, which is supposed to run on the job control system, and is frantically pinging it, asking, can I start now, please? But the job control system wants to make sure it's safe to start, so it's asking the authentication server. In a disaster, all of that will just sit there forever until a human figures out how to unwedge some of it. But it doesn't have to be this way. We can prepare for disasters and bootstrapping. We can design and operate our systems in a way that makes them more reliable and makes it possible to restore them after a disaster. We do this two ways, by managing our dependencies and by reducing the need for fallback plans. The first step is getting a global picture of what depends on what. Like everything in the world of SRE, this starts with monitoring. To start with, you just gather the information. You might not like what you find, but you really need to know. When we started doing this, it spawned a whole lot of conversations that went like, no, we don't use that. Are you sure we use that? Why do we use that? Oh, we should stop using that. Let's watch this in action, collecting dependency data for a made-up application that does something important. It displays pictures of cats on the internet. You've got cats, you've got people who want to see cats, but you want to serve the right cat, obviously. This is a made-up snippet from a made-up design doc that you should not use to implement anything because it's nonsense that I wrote on the subway. Okay, first design doc. An in-memory index of the available cats with some metadata. There's a cat chooser that uses information from the user's request. There's cat attributes. There's an index for cats that matches attributes. We pull the cats from storage and return one to the user. The index is run at startup and at intervals to update the metadata, make sure we have accurate sentiment analysis and geolocation data for the cats. Because it's the worst when someone wants a happy cat and you serve them a sad cat. Like, users hate that. So we launched this incredibly successful product, venture capitalists just beating down the door, and then the product manager files a bug. We're occasionally serving pictures of raccoons. Users hate that. They want to see cats. So we add a catness analyzer. We've got a whole user story about it. Cats must be cats. And this is just a snippet from the design doc. This isn't the whole design. Cat analysis is an expensive operation, so we don't want to run it on all of the cat pictures. We are going to take the index from the cat user, run catness analysis. Unless you were the best kid in your class at reading comprehension, you were like, that design sounds awesome. Bring on the cat analysis. This is an amazing service. I see no downsides. But if you have a way to discover the dependencies, you get to think about whether it's a safe design. So here's the dependency list. It says, like, the web server depends on the cat chooser, and the cat chooser depends on the geotagger, and so on. This is better, but it's still rough for a human to make decisions about. We need pictures. There are a lot of really good ways to make dependency graphs. For example, Netflix has a visualization tool called Visceral, which is really beautiful, and I recommend that. But most of the time, I just use GraphViz. I love GraphViz. So look at this. This is a valid GraphViz config. If you have basically no time to spend on visualization, you can construct a GraphViz graph. I'm just going to geek out on GraphViz for a few minutes, so please bear with me. But this is the complete config for this important application. Digraph means put arrows on the graph. Everything else is a list of dependencies. And here's a picture. There's the command line at the top, the GraphViz package. If you don't have it installed, we want the picture in PNG. And there it is. Humans can understand this now. Humans can be like, what's the deal with the cat user and the cat analyzer, the catness analyzer, depending on each other? If they go down at the same time, might the cats go away? And this is an important question to ask. The answer is yes. So I don't know. There are fancier ways to do visualization. But if you want something you can get your head around in a couple of minutes just to make sense of some data, GraphViz is fantastic. But where does this data come from? I mean, in this case, we mined a design doc, but that doesn't scale at all. It doesn't work very well. Anytime that a human is sitting down drawing boxes, either by, comprehending text or just remembering things, you're going to have a bad time. Human brains are awful. Human brains are basically the worst kind of storage system. We're low fidelity. We're really lossy. Ideally, you would like one of the reliable robots that's going to take our job to do this instead and keep it up to date. So where can you get this data? Can your monitoring system tell you what's going to where? That's what we do, by the way. We instrument common libraries, and we export all of the dependency information to our monitoring system. If you can't do that, there are alternatives. Like, do you have network devices, or load balancing, or a service mesh, or a name resolution server that knows everything that's going to everywhere else? Are there structured logs you can run queries over? The more standardized your infrastructure is, the easier it is. So one thing you should be objecting to at this point is that all those mechanisms I just listed, you're not going to find out about the cycles until the binaries are already running. And it's a bit late at that point, isn't it? Ideally, you want to prevent them from happening in the first place. And we can do that. We can set rules about what can talk to what. No, the authentication system can't depend on the front end. That makes no sense. That's a terrible idea. So my advice is to lock this down early with rules, earlier than you think. Systems grow and evolve, and distributed systems rarely get simpler. Even if you know for absolute certain, stop bothering us, Tanya, we know our dependencies are fine, even if you're certain of that, it's good to be prepared and set rules about what can depend on what. At the very least, have a bunch of policies. Don't make people have to reason about it every time. Like, you must be this tall to use DNS. DNS is a dependency, by the way. I think a lot of people don't really think of it because it's a systems call and it freaking always works. DNS is, except when it really doesn't. But DNS we sort of forget about because it's just magical name resolution, right? But where do your DNS records come from? Where are they stored? What could stop you from changing them? DNS is a real dependency. Anyway, write a bunch of policies. make all of your design docs for new systems have to explicitly list all of the dependencies and whether they follow the policies. But what's even better than policies, if you're feeling fancy, which I recommend, actually make it impossible for things to contact services they shouldn't. So we've built this into our RPC library. It's a thing, it's kind of like an ACL, an access control list, but it's going the other direction. It's on the client side. So whenever anything wants to send an RPC, it first calls a method to check if this is an expected dependency. This is extremely fun code for my team to write because it has to be really fast. But it's not very much code. It's an easy thing to add. We roll this out in monitoring mode first. So if you send an RPC to something that you shouldn't, we increment some monitoring variables. We optionally let you alert on it. We open a bug, you get paged if you really care. But later we flip a switch and we fail RPCs that are going places where they shouldn't be. It's pretty great. And it encourages people to have really good canaries. If you use Kubernetes, you get something like this for free. I'm new to this, but I've just been reading about the Network Policy API, which I think went GA this summer. And it lets you enforce policies about what services can talk to what other services. This is a config snippet I grabbed from kubernetes.io, where they're demonstrating how to limit access to an Nginx service to only things that have the label access equals true. Anyway, if you don't use Kubernetes, there's no need to bother parsing that, but I'm just including it to show an alternative approach. Network policy, I think, operates at layer 3 and layer 4. We're operating at layer 7, but there's a lot of different ways to do it. If anyone knows any other implementations of this sort of thing, I would love to hear about them, because I'm really interested in how other people do it. So maybe give me a shout on Twitter or talk afterwards if you know. I'd love to hear. Anyway, one thing you come across whenever you do this is soft dependencies or optional dependencies. These are services that are useful, but they're not essential. So people will argue that they're not really a dependency because you don't need them, so you shouldn't have to think about them, right? For example, everyone should be able to start up without their monitoring system, you would think. And if that's the case, if they're like really, really actually not dependencies, then maybe this is okay. But then you have to make sure that they're as soft as you think they are. Like, you know, we consider the monitoring system to be a soft dependency, but then people build health checking checks on top of it. And their load balancing depends on it. So if you do have soft dependencies, I recommend doing regular tests where you just turn them off and see who screams. It's scary, but you can do it. That's what error budgets are for. Give people warning that it's going to happen, but if they can't manage without them in a controlled outage, they can't manage without them. If they need the dependencies, they need to decide what happens if they go away. Which brings us back to fallback plans. Whether you're trying to recover from the failure of one server or trying to bring your whole site back online after a major disaster, the fallback plan needs to not have many moving parts. It needs to be the tightest, most tested, most badass procedure you have. And the fewer of them you have, the better. Reserve parachutes are a really great model for fallback plans. So the deal with reserve parachutes is a skydiver might do a bunch of different jumps in a single day. And if they're repacking their parachute after every jump, they may get tired, they may get sloppy. So if you're a skydiver, you carry a reserve parachute. It's sealed and it's carefully isolated from the main one. And you try to never use it. But the deal is you don't get to decide what your fallback plan is. The law is that you carry a reserve parachute. You don't get to decide yourself whether, you know, this is actually important. Maybe you've got a better idea. Maybe you've got a little fancy umbrella. You don't get to think about this. This is the fallback plan. And the other thing about it is that it's packed by an expert. It's not packed by you in the past. It's packed by somebody whose job is packing reserve parachutes. So you can trust your life on it. Model your fallback plans like that. Again, maybe you think your site is too small to care about any of this. Believe me, if I could go back in time, I would have us do dependency management much, much earlier than we did, like maybe 1998. It's trivial to start when it's easy to reason about, and it's less so when you have a spaghetti tangle of horror that you need to comb out, which we at Google have never had to do, for the record. The other good thing about starting early is that you can design your systems to be bootstrappable from the start. You can set some simple rules, and you can architect your systems on a model that's fundamentally bootstrappable. Layers. Not OSI layers, by the way. Layers like rock strata or clouds. So here's how layers work. You divide your stack into sets of things, each of which can completely start up and run without anything below it. Here's your first set of jobs, here's your second set of jobs, here's your third set of jobs. Like maybe network and then authentication and then storage, but it really depends on how your site is built. you can architect all of the new systems in layers. It means you have to socialize this idea in your organization and make people think about it and buy into it. But if you do that, you can have everybody who's making something new think about where in the stack they sit. You can give if you don't have many layers, you can give them names. People will think, oh, I guess the front ends are above infrastructure. You've got a few, but if you've got a lot of them, then maybe you want to give them numbers. Maybe you want people to have to look this up. And again, if you're feeling fancy, it's good to feel fancy. You can enforce it in code. So you can have your code say, hey, this layer 500 thing is contacting something that's layer 750. We should alert them, or maybe even block it. People will always say, can I go up the stack for soft dependencies? And mostly I would say discourage it, because every single exception adds cognitive load. It's an extra thing you have to think about. It's an extra thing that you have to test. Mostly I would say don't force humans to think more than they have to. So if you can, make things either real dependencies or don't use them, or split the functionality so that most people are depending on things that are below them, and you have a tiny number of soft dependencies that go up the stack. If this is rock solid and reliable, you know what you have? You have a stack. We're back to an actual stack. And if you have a stack, you can have a social contract. And if you have a social contract, you can go back to just knowing the parts of the world that you actually want to go deep on. It's very reassuring. Last thing, even with your layered architecture, your managed dependencies, and your teeny tiny fallback plans, it's good to occasionally test that you haven't missed something. Like, are you really able to restore the service if it all goes down everywhere in the world at once? Can you turn your company back on after a global reboot? The best laid DR plan can be missing something critical. Unfortunately, or probably fortunately, most of us don't have the luxury of actually turning our sites completely off and on again. That would be really exciting, wouldn't it? But we do have to test. And ideally, most of the day-to-day testing will be done by the smart robots who are taking our jobs. But it is worth doing real-life disaster simulations with humans, partly to make sure we know what to do, but just as much to make sure we don't freak out when it happens. One of the nice things about automating your testing is that you can build tools to do it that are useful during a real recovery. So if you can make your testing tools do something that is useful, that you use for regular operations, that's even better. Like, say you're building a new site, you're moving to a new data center. Can you turn that up using your DR process and try not to touch anything in your primary site, pretend it doesn't exist, and see what works, and see what doesn't work? That's going to shake out a whole lot of things that you wish you had offline. And this is a great time to do it, because right now you can get them, you can have them offline. So you may find out that there's some passwords you don't know, maybe you need installation media, maybe you need keys, maybe some binaries, maybe some configs, maybe some documentation. All the stuff you needed to go back to your primary site to get. My first job's bootstrapping material was a bunch of Solaris CDs and some passwords which were written in a sealed envelope, at least it was sealed, in the sysadmin's desk drawer. And that's not what we do at Google, just for the record. Whatever it is for you, understand what you need and make sure everyone knows how to get to this information, or at least everybody who would be involved in a major global disaster. But again, work on making this as small as possible, because it's a fallback plan. And that means it's bit rotting from the moment you put it into place. So, right, I just said a whole lot of things. But if I get to have you take anything away from this, here are 4 conclusions I would like you to please consider and maybe even take away. As much as possible, make your emergency plan follow a well-trodden path. Code, systems, processes that only happen very rarely, they're likely to bit rot and get buggy and not work when you need them. It's the backup generator problem. It probably doesn't work anyway, but even if it did, no one remembers how to use it. Have a well-defined way you want your users to react if a piece of infrastructure goes away. A bad fallback plan is sometimes worse than no fallback plan. In case I haven't said it enough times, anything you haven't tested won't work when you need it. The middle of a disaster is no time to find out that you can't reinstall some application or that you don't know how to get into your fire safe. And again, if you don't test your entire backup process, including putting the data back in the database, you don't have backups. Even if you think your site is simple, understand and manage your dependencies early. At the very least, discover and expose what they are, and ideally have policies on what can depend on what. Make dependencies a part of the design conversation. Have rules. Be super opinionated. Say no to special cases and one-offs and things that humans will have to think about. Don't force humans to think. Hold the line. And protect yourself against future dependency chaos by putting a structure in place early for bootstrapping your system in layers. Again, do it before you need it. long before you need it. And really push back on optional dependencies in special cases. Build in alternatives that make it as easy as possible for people to do the right thing. I feel like 37 people have already said this at this conference, but I made this slide before I came here, and I'll be number 38. All of this can be summed up with the motto of Google SRE, which is hope is not a strategy. And it applies as well to disaster recovery as it does to most things. And that's all I have. Thank you very much.